Let's start the serious stuff. So, as the first speaker, we welcome Weizhe Wang from Shanghai University, who will talk about a new differential fault attack framework called Shortcut to Secrets.
Yes.
Please.
Okay, thanks for the introduction. Good afternoon, everyone. I'm Weizhe Wang from Shanghai Jiao Tong University. It is my great honor to give a presentation about the shortcut to secret here. This is a joint word with Pirik Mills and Dentang. Okay, my talk consists of 4 parts, and I will first begin with an introduction to the differential fault attacks. Proposed in 1997, differential fault attacks are a powerful class of side-channel attacks. In the DFA, the attacker will inject force and try to use the correct and faulty output to extract sensitive information. For example, the attacker can use the difference between the correct and faulty output to filter out some wrong key candidate. For the fault injection, there are many mutual techniques. For example, the clock glitch, voltage glitch, EM+, laser beam, and et al. For the fault model, there are bit freed, word, byte, nibble error, which can be random or deterministic. In our work, we mainly use the random nibble error model. And for the DFA to work, we usually assume that first the cipher can be restarted with the safe parameter, and the fault injection timing is controllable. The attacker has the corresponding fault injection tool, and the number of faults should be limited. Since its birth, the DFA has been widely applied to many symmetric key cipher, including the AES and the Trivium. Though the DFA is powerful, it is tailored to the specific primitive, which will require deep structural knowledge of the target cipher. The Elizabeth IV cipher is a new stream cipher designed for the hybrid homomorphic encryption, HHE, or we call the transciphering. The Elizabeth IV follows the group filter permutator paradigms, GFP paradigms, which is greatly different from the previous methods like LFSR or NLFSR. This new design makes the previous DFA methods inapplicable to the Elizabeth IV. And in last years, Wang and Tang proposed the first DFA on Elizabeth IV, which was published at the IEEE Translation on Computer 2025. But the previous attack is quite crude and only intended for Elizabeth IV. Hence, we don't know whether the attack can still work when we target other GFP ciphers. Moreover, the existing word remains largely at the experimental stage and lack the theoretical analysis. So if we can give a theoretical analysis, we may better improve the attack. Building on this, we make this work. First, we present a table-based differential fault attack framework called shortcut attack, which generalizes the previous attack and applies to a broad subfamily of cipher that follows GFP. Second, we enhance the previous attack by improving 2 steps in it. Thirdly, we provide the complexity estimate for the shortcut attack framework and apply the framework to Elizabeth IV and its patch. Finally, we also try to derive the security margins to prevent shortcut attack on a broad subfamily ciphers follows mixed filter permutator paradise, NFP paradise. Here comes the attack result. You can see that we improve the previous attacks on Elizabeth fault. We also give the first single fault DFA on Gabriel fault and Elizabeth B fault. For the Margaret 80 fault, we give some multi-fault DFAs. That's the result of our attack. Okay, I will introduce the Elizabeth cipher and its patch versions the next. Okay, first I would like to introduce the GFP paradise. In the GFP paradise, at each iteration, PRNG is updated, and the output of PRNG will determine some public elements, including a subset Si, a permutation Pi, and a widening vector Wi. Then, some element will be selected by the subset from the key register and then permuted and added with the widening vector W. And finally, a filter function F will be applied to the state and generate the corresponding keystring element, just like the picture show. The Elizabeth 4 is the GFP cipher instantiated with a group C16, and the length of the key register is 2056. At each type, it will select 60 elements from the key register. The filter function of Elizabeth 4 is the direct sum of 12 times the 5-to-1 function G, and we call the function G the inner function. The inner function G is also a sum of a nonlinear 4-to-1 function H and the remaining variable. This construction is special, and the patch version of Elizabeth 4 also take this construction. And this is great important to our shortcut attack framework. Unfortunately, at Asia Crypt 2023, the Elizabeth 4 was broken by a theoretical algebraic attack. As a result, Hoffman et al. Proposed 3 new ciphers. They are Elizabeth B4, Gabriel 4, and the Margaret 84. The Elizabeth B4 is also the GFP cipher, but instantiated with the same group as the Elizabeth 4, but with a larger key register and a larger subset. Correspondingly, the filter function of Elizabeth B4 also become more compressed. It is the 14th type of the 7-to-1 inner function G. For the Gabriel 4, it can be seen as hybridizations of Elizabeth 4 and Elizabeth B4. It means the filter function of Gabriel 4 consists of the inner function come from Elizabeth 4 and the inner function from the Elizabeth B4. Okay, then is the mixed filter permutator paradise. The NFP is actually the generalization of GFP. The string ciphers that decide following the NFP paradise will take a secret key from the group 1 and output the secret key over group 2. While in GFP, the group 1 and group 2 must be the same. And the Margaret 84 is the NFP cipher instantiated with the group 1 is the F2, like it was over bit, and output key string over C16. The length of its key register is 2048, and you will select 308 elements at a time. The filter function of the Margaret is also 14 times of the inner function G, but the inner function G is the sum of the nonlinear function H and C16 transformation. It will transform 4 bits into an element of C16. That's what NFP like. Okay, after introducing the cipher, let's dive into the shortcut to secret framework. First, I would like to introduce the target of our framework. Our shortcut DFA is drawn for a subfamily of cipher that follows GFP paradise, and the filter function are the direct sum of functions in a smaller number of variables. That's why we call this subclass of cipher the DS and DS GFP cipher. DS means the direct sum. Specifically, the filter function in DS GFP cipher can have some different inner function GI. For example, the inner function, the filter function of Gabriel has 2 different inner functions, while Elizabeth and Elizabeth B already have 1. Okay, our shortcut attack actually consists of 3 steps. This is also a common procedure for the DFA. First, we need to inject fault and collect the corresponding output key string. The second step is to identify the fault, and finally, we need to recover the secret with the fault. Due to the structure of GFP, we can identify the fault quickly with 2 useful tools, and I will give the detail later. But for the key recovery, for the key recovery, we cannot just build and solve equation concern the secret key Kate, because the inner function G of the DS-GFP cipher are often decided without polynomial representation over G. Therefore, we need to use a filter table T, which is similar to the DDT, to help us filter out the wrong key. And the filter table T is actually about the nonlinear function H. It consists of the input variable and the input difference information and the corresponding output information. Okay, I will give the detail about how to identify the fault. First, let's see what a fault will affect. Without loss of generality, we can just suppose the fault is injected at K1. And due to the GFP paradise, the fault will propagate to the state and affect only at most 1 stage xi per iteration, like it will affect the input of H or just the linear variable, and finally propagate to the output key string. So what is exactly the effect of a fault? First, if the fault is not included in the subset, we will definitely have the output key string difference is 0. When the fault is included in the subset and it falls in the linear path, we will have the output key string difference is exact the fault value. Otherwise, if the fault falls into the nonlinear path, we will get an equation that delta Si is just equal to the difference of 1 nonlinear function H. Okay, based on the effect, we can get the 2 useful rules. The first one is that if the output key string difference is non-zero, we can know that the faulty keyword must be included in the subset Si. And the second rule is also a new rule we propose in this work. That is, if the output key string difference is 0, we know that the faulty keyword will not appear in the linear part because the fault will be all non-zero all the time. Then we can use some key string and the 2 rules to quickly locate the faulty keyword. When the for the keyword is located, we can directly obtain the values, the corresponding fault value according to this loop. Yes. Then, after determining the fault, we need to recover the secret information with fault. In though TS-GFP cipher can have some different inner function JIT, in our shortcut attack, we only use the one with the fewest variable and denote the number of variable DM. When the fault falls in the nonlinear part, we call the corresponding keystring the valid keystring, and we can have an equation like this. With this equation and pre-computed filter table, we can use the fault information and the output keystring difference to filter out a candidate set for the state element X. On average, the candidate set will be, the size of the candidate set will be the cardinality G to the power m minus 1. Then, given the value of X, we can calculate the corresponding value of key according to the GFP paradigm. And in particular, for each valid key, we can get a candidate set for m key element. And here gives an example of the information we obtained. It can be seen that though we can get the candidate set, but the related key position we obtain each time will be different. Just like the second line and the third line, the I is different. So how to recover the correct secret key with the obtained information? A natural idea is to find multiple valid key strings whose I are exactly the same. And we just need to intersect their width, and we derive the unique correct key, a correct value. But this method will require a large number of key strings, and it is impractical. So we propose a new method called merge and intersect. This is because actually even the related key position I are different, we can still intersect them and merge the I to generate a new I. For more detail, given two index sets S1, S2, we can merge and intersect and obtain a new set. The new I is the union of the original two, and the V is the intersection of V1, V2 at the common index and concatenate the least part. For better estimate the candidate set size, we propose a proposition to calculate it. It can be seen that it is related to the number of common index, and this will be useful in our attack. Okay, with enough valid key strings, we can just merge and intersect iteratively and finally obtain the unique correct key. During this process, the I will increase until all key elements are included, while the candidate set V will expand rapidly at first and then slowly reduce until the unique right key is obtained. Here, a key issue is that the order of merge and intersect. For the key recovery process, our main operation is the set intersection, and the complexity for this operation is directly related to the size of input set. If we just randomly choose a path, it may lead to a large candidate key set and exceeds our practical limit soon. So in our framework, we need to find a path that minimizes the candidate key set. And that's what the shortcut means. Then how to select a shortcut? A simple idea is just to minimize the set at every type. And this comes to the simple greedy algorithms. But the original greedy algorithm is not so good, and we enhance this process by proposing an improved method called multiple initial point greedy algorithm. And the idea is very simple. For the original GA, we just choose one initial point and generate the corresponding path according to the greedy algorithms. But in NIP G8, we will prepare some initial point at first and use the greedy algorithm to generate paths for each one. And finally, we will just compare them and choose the one with the minimal as mass. And here comes the detail of our shortcut attack framework and the corresponding type complexity. It can be seen the 5 steps recover the secret according to the match path will domain the whole attack. So it is critical to select a proper matching path. And we make some experiment to compare the performance of different greedy algorithms. You can see that our new NIP greedy algorithm greatly outperformed the original one. Okay, we also try to apply our shortcut attack to the Margaret 84, but the MFP paradigms and the large key space prevent us from some single fault DF8. But we can still make use of the Z16 transformation to recover some key information with the fault. And based on these equations, we present 2 different multi-fault DF8 on the Margaret 84. Besides the attack, we also try to give a theoretical analysis to see how the general DSGF NFP ciphers resist our shortcut attack. In particular, we derive a security limit about the number of key strings, the SL. And if the available number of key strings is less than the SL, then we cannot generate a proper merging path, and the candidate key set will increase rapidly, which will make our shortcut attack invisible. We compute SL for the 4th cipher, and we can see that the Margaret 84 has a rather large SL, and that's why we cannot mount a single fault DFA on it. Okay, finally, I will summarize my lecture. What we did in our work, we just generalized the previous attack into a framework called shortcut attack, and we enhanced the previous DFA by improving the identification step and the path generalization paths. Moreover, we give a detailed complexity estimate for the framework and give the first DFA results on Elizabeth 4, Gabriel 4, and Margaret 84. Finally, we also try to explore the feasibility limit of the shortcut attack on the general MFP ciphers. Finally, I want to give some open question here. The first one is, can our shortcut attack be adapted to the cipher whose filter function do not relate on the DS? The second one is, can we improve our attacks by investigating the construction of the linear function H? And the final one is, recently the SASTA framework was proposed, and they can use the HHE protocol to execute the DFA. So our question is, are there other ways to use the higher order protocol to enhance the existing attacks or just develop some new attacks? That's all. Thank you.
Thank you for this interesting presentation. We are running a bit late, so perhaps when I take just one short question. No? So perhaps I have one. Do you think that your framework could apply to other similar algorithms?
Yes, actually this is the first question we live here. And though in this work, we target the DS-GFP ciphers, but actually there are some GFP cipher who use like the threshold functions, and it may use some other fault attack technique. I mean, we may not use difference, but some other like statistical or some other methods.
Okay, interesting. Thank you. Let's thank the speaker again, please. Okay, so now we want to listen Fan Chang, who will present a new fault attack on ASNI instructions. So please.
Okay. Thank the session chair, Victor. Nice to meet you. And thanks for all for being here. Good afternoon. My name is Fan Zhang. I come from Zhejiang University. I worked on the side channels and fault attacks. Now recently I put more efforts on the fault attacks. And in 2018 I proposed a new attack called the persistent fault attack, PFA. And today I would like to present a new work called OFA. So practical opcode-based fault attack, and the target is on ASNI. So the technique we used here is using the row hammer. So here is the outline. We do the background, and I will talk about the attack, the details, and some experiment, and also the summary. So first, the introduction. So fault attacks are very important in the area of, I think, implementation or with cryptographic engineering. It introduced some like hardware faults, and in order to get the secrets of the ciphers that's running on it. So it has two stages, and the injection and the analysis. The injection ranges a lot of techniques. For example, the clock glitching, and lasers, and row hammer. And analysis techniques including like differential fault analysis and statistic analysis. The ultimate goal is to try to get to analyze the output and finally extract key. So the target of our work is on the AES algorithm, which is very important. And to make the AES fast and secure, so Intel introduced ASNI. It's a set of CPU instructions. While ASNI is very effective against side channel attacks and like timing analysis, but its resistance to the fault attacks is not that clear. Should be put into well discussions. And the previous, I think, fault attacks requires a physical access or some like privileged controls on the voltages. So these injections may not be that easy to the AES-NI that is resides in like a normal PC or laptop. And our work try to explore a new and more practical method. So let's briefly look at the AES instructions, and there are 6 of them. And the most, I think, the important of attack focus on the encryption and the decryption part. So the first 4 instructions, named as AES-ENC, AES-ENC last. So we know AES has 10 rounds, so the first 9 rounds, it use encryption for the 4 round. Use this instruction, AES-ENC. And for the last one, it lacks a mixed colon, so we call the instruction AES-ENC last, as the name says. So the figure here, on the left, I think it's AES encryption, the 4 round, and on the right, so it's used for the last round. And our injection method is based on the technique called Rohammer. I like this technique very much because it's first software intrigued, and eventually it caused like a hardware error on the target. And basically, it changes like the electromagnetic, like the phenomena among different rows in the DRAM, and it can cause some like bit flips for some rows in the data side. So in this talk, so I use this bit flip, try to flip some opcode of the CPU instructions. So this is the techniques we are using. Rohammer has been there, I think, for many years, and nowadays it can be work very efficient on, I think, DDR4. Now we move to our attack. Sorry. So here is the core, I think, the discovery for my talk. So we analyze the instructions for AES-NI. So we list the opcode. Among the 6, I think, different instruction, actually we find different pairs. So here we find 6 different pairs. And so for the first one, so AES-NC and AES-last, when you express all things in the binary, I mean the opcode, you will find there are just only 1 bit difference among the 2 instructions. So basically, if you have the technique to flip 1 bit, and you can change for example, the instruction in the last round, and can change it to the AES-ENC. So basically, this is a core idea. And in that sentence, so all the 10 rounds of AES will be using the same round function, and this will be causing some like issues in the cryptanalysis. So I think I already just mentioned the core idea. Okay. Solar model, so attack has a very low privileged user on the same machine, and they can send the encryption and get the output from the ciphertext. And also there are the assumptions that the underlying machine is using the DRAM. The DRAM is vulnerable to Rohammer attack. Okay. And the goal is very simple, to get the key from the victim. So here is a high-level overview of OFA targeted on the AES 128, and one performs the correct encryption, and the other executes, I think, a 40 AES encryption. And this is a diagram. So on the right, so there's a injection, changes previously there's no mixed column. So if you inject the fault, basically it equals to a 4-round AES. And this happens to the last round. So this is normal one, and this is the 41. Since it equals to a 4-round of AES, basically in the last round, suppose X is input to the to this stage, and you introduce the mixed column. Basically, it's the state will multiply matrix for the A. A is here is a fixed, I think, a matrix. Use the traditional mixed column. And eventually, I think you have a pair of, like a traditional fault analysis, you have a pair. One is C, which is correct, and C prime is incorrect, and then you try to do the analysis. And the analysis here is also very simple because these two are combined with equations, and solving the equations is relatively easy. Okay. So yeah. Oh. Okay. So here you can see. So this is the correct one. So the state here equals the key. And this is the incorrect one, basically equals to multiply matrix called A. Then for these two instructions, these two equations, you simply do like a XOR or subtraction. And here, the Kn and the Kn are canceled. And then eventually you simplify this one. You get a very simple equation. On the left, A, XOR, I. I here is actually an identity matrix. C, XOR with C prime. So all these A, I, and C prime, C are known. Then basically you figure out a way to, you put some like solutions on how to get the X. And since X is constrained by the matrix A here, the complexity is relatively, I think, low. It's 2 to the power of 32. And that can be done within a very, I think, on a normal computer. So that's the core idea. Okay. And we implement all the like end-to-end attack on 2 platforms. One is with DDR3, one the other with DDR4. And we try to run the first injection, and then to do the analysis. We want to verify that all the 2 steps here are practical, can be done within a practical time. So this is some little bit details on the Rohama attacks. The first step, you do the profiling. Profiling means that you have many different pages, and the first you need to know where the vulnerability is. And these are the 2 like the adjacent pages, and these are the victim bits that we can find. So the memory we are using is, I think, relatively vulnerable and easy to find the bits, the flip bits. And this is the index of the page, and it's index of the, I think, the unsigned int. So it's 64 bit. So this is which 64 bit. And among these 64 bits, and what's the index of the bit? So it's 55, something like that. So this will give the details of where the bits is located inside the page. And rowhammer, basically the core idea is so you put the data in the different rows, and you read from the top, the row on the top, and then you read from the one on the bottom, then randomly, so you will have the chance to flip one bit for the row in the middle. And then you try to repeat this process, and you put the vulnerable page inside and try to see what's the percentage or the probability you can put the page, the data on this process. And the second step is basically try to put the page that contains the opcode, and try to do this one on the rowhammer. So basically, you try to fault the opcode there. Okay. And the last step is basically try to recover the keys. And how to recover it, I already mentioned in the previous slides. And we try to analyze how our OFA work on the different scenarios. And the first we do something like the ECB, the electronic like code book. This is the mode for the AES, and we run the experiment. So we try to inject the bits, which is called online. So around 14 hours. And after that one, we do the analysis, so roughly 1 hour. And the complexity, as I said, is a reduced time, reduced to the 2 to the power 32. So compared to the 4 key size, 2 to the power 108, and we reduce about 2 to the power of 96. And meanwhile, we try to explore the different mode called CBC mode. And there are some slightly difference between the mode using, because sometimes it has the initial value, sometimes it's without initial value. And we discuss the details in the paper. Okay, some other extensions. So we explore the case for the 192. And the core idea is that, so for 1 bit injection, probably it's not enough. Then we try to find different ways to inject more bits in this case. Okay. So finally, the conclusion. I think the idea is very simple, and the analysis, since it's a mixed column, so it's just simply a brute force. Sorry, it's equation solving. So I think the contribution are from 3 aspects. The first, we discovered vulnerabilities in AES-NI. It's more on the implementation of AES-NI on the instructions on the software level, because the instruction calls the underlying hardware. So I do believe this is called software intrigued attack, which matches, I think, the concept of rowhammer. Second, I think we give the idea how to do the analysis, which is quite simple. And third, we do end-to-end fault attack. We do the injection, also we do the analysis. So previously I mentioned I do the PFA, persistent fault analysis. The basic idea for PFA is that it injects 1 bit flip in the tables of like a AESA. So I said this probably can say it's a positioned like a data-oriented photo attacks. In this work, we propose OFA. It's at an instruction level and focusing on the opcode, and we give the name as OFA. So I think probably PFA plus OFA will very likely, I think, cover most of the scenarios that we can use in the photo attacks. Okay, that's all. Thank you.
Thank you very much for this interesting work. Do we have any question? Yes?
Thank you for the presentation, and I think this excellent work.
Thank you.
My question is, I think the main concern is how to get the location. Is it?
Yes, yes.
How to get location, and is it independent of the table, the page and page table, and all the TBAs, and from the conversion from the virtual memory to the physical memory? Is it this opcode is independent of type of that?
No, I don't think it's independent. I should
Yeah, I
depend
mean,
on.
there are ways that you can change from the virtual memory to physical memory, right? In Intel.
Mhm.
So, is it the opcode? This solution is independent. Mean you can use any type of Intel processor to get the fixed location of the memory. Do you understand?
I think this one is the most important part is that you have get the vulnerable the memory.
Means you can use this on all Intel processor.
Yeah.
Okay.
So I think we choose some like a different two laptops and try to say this is quite general, but the general means the processors is general, but the memory should it's not that general. You need the vulnerability there.
Okay. Thank you. Congratulations.
Did you contacted Intel about your work before publishing?
Probably no.
No? Okay.
Because I think this is not the fundamental, I mean, the problem with the AESNI. It's the implementation. But probably I think about this one. Probably we need to give the advice for Intel because they designed such a library, basically different the design of instructions. So try to say when you design the instructions, try to avoid the case that the two instructions with very similar or 1-bit or 2-bit difference. So
Yeah.
this is probably, and this is for the ASNI. And actually, I think, but we didn't continue, but I think if you try to invest all the instructions in the, I mean, Cross 86, the instruction set from Intel, probably you will find some vulnerable design, I think. And this one is not just for Intel, because if you're saying ASNI, it's not just for Intel's, right? We also have the ARM, so probably you have.
Yeah, and AMD also, I guess.
I guess so. Also RISC-V something.
Is there any more question? Yes?
Hi, thanks for your talk. I'm a little confused since you haven't presented any results. Did you actually do this, or
Yeah.
is this an idea?
I think we did this. So the paper, I think, that can be accepted in CHES, and I think with the two contributions. The first is the analysis part is relatively easy, and during the review, actually, we showed a lot of results on how we inject for the opcode and we do the fault analysis. Yes, we did. We did this one on the first, the two platforms there. Also, I showed the time for the injection and for the analysis all within, I think, 1 hour. Yes.
Okay, thank you. I'll definitely look at the paper. I have another question. So in order to mount the attack, you have to compare the expected output of the AES operation with the faulty operation.
Yes.
So you need to have access to that memory.
Yeah.
So what prevents you from stealing the key from that same memory?
Not from the memory, because that one is the C and the C prime are actually the output, the ciphertext. So it doesn't require that it should be on the memory. Right? Eventually, you do the encryption, so you will give the output to the normal users, also including as I think the adversaries. I'm not sure whether I answered the question.
Yeah, yeah.
So this is a
you don't need to be privileged. Your adversary program, it can be just at user level to apply the rammer attack.
Sorry, say it again.
Your program applying the rammer attack doesn't need to be root.
No.
So yeah, so then
we don't need the root. So I said we are just the lower privileged, basically I think normal user, and the interesting for Rowhammer is that you can read from the row above and on the bottom, and you get a 1-bit flip, which means you have the right privileges. Yeah, so that's the essence of Rowhammer. Yeah.
Yes, but in order to see the result of the fault that you induced, you need to have access to memory, and you say that's from an unprivileged account. So you need to be able to look into the process space.
I don't think we need to access the memory, because we just see the eventually the output of the C and the C prime. So that's.
Okay, I'll just read your paper. Then.
Okay, thank you. Thank you.
Thank you. So let's thank the speaker again.